Swayam Prabha. Digital India. Educated India.
Welcome. So, this is the last lecture of this module. Here I will discuss mainly a small problem and one just extension of what we learned in the last class. So, this will be the last lecture of this module. So, we almost finished it. Here what we have learned in the last class is essentially finite element stiffness matrix and especially the geometric stiffness matrix we learned. So, geometric stiffness matrix, how to compute it, which gives generally the P delta effect in building frames also. So, the basic premises of this is your beam column equation from which we derive the weak form, and then by discretizing with standard beam element that we have learned in this module. So, using that Hermite shape functions, we finally computed the element based stiffness matrix or element based geometric stiffness matrix. So, in addition to the beam stiffness matrix, geometric stiffness matrix is also there in the beam column equation, because in beam column you cannot neglect the axial shortening of the column due to the axial load. So, here the basic governing differential equation for this is your d square d2 dx square ei, that is the bending part. So, d2w dx square plus p critical, that is critical buckling load d2w and dx square. So, that is equals to 0 and appropriate boundary condition. So, boundary condition will also have a force term that we have seen in the last class. So, here what I plan is that in the last class we have discussed one small problem, that is your a cantilever column, finding out the critical buckling load, and we solved a one element solution. We found that a one element solution. So, here also we will try a simple problem, because if I just increase the number of element, it is just a repetitive, and based on the element assembly your solution final matrices will be in higher dimension. So, let me just put the problem first. So, this is a simply supported your pin column. So, I can just put a ruler here. So, or pin beam you can say. So, here if I have a force P, then what will be the critical force for which the buckling of this beam will start. So, that is the critical buckling load. So, now the objective is to find out the solution of this, or finding out the critical buckling load of this problem, and for which we will solve this eigenvalue problem. So, now we know that the element based equation for this problem is we already knew, which is K beam stiffness minus. So, I am just not repeating what we have learned is in the last class. So, here is my pre-critical. So, P critical is my buckling load, and then you will have our Kg, which is geometric stiffness matrix, and then your W vector, that is your rotation and displacement, generalized displacement. So, that is equals to your force vector. So, this is the eigenvalue problem. So, here obviously this term will be 0 essentially, because we are doing a eigenvalue problem. So, simple problem and simple beam. So, here if this simply supported beam, then this beam will actually buckle like this, something like this. You see, this beam will buckle like this. So, if I want to analyze the beam, I can simply do 1 element, 2 element, 3 element, 4 element. Likewise, I can do the solution. But suppose if I want to solve this beam in 2 element, element 1 and element 2, I need not to actually do the 2 element formulation. Essentially, I can analyze the half of beam and then find out the critical buckling load. Because if I just draw the free body diagram at a certain intermediate stage, then this at this half of the beam essentially will have this force P. So, that is the free body diagram. So, now I can consider only one element, then one element equilibrium equation I can consider. So, now you know also the boundary condition for this. So, if this beam is L length, that is L is my length of the beam, then the boundary condition W is 0 here, W is 0 here, this is 0, and the moment, that is EI d2W, let me take EI constant, this is also 0 here, and x equals to 0, that is EI d2W dx2 at x equals to 0, x equals to L is 0. So, this is a simply supported essentially the beam, and so what will be the boundary condition here? So, naturally here we know the slope is 0, right. So, slope will be 0. So, that is the our boundary condition. So, if I try to analyze the beam, I can take this end also. So, now this node, if I take the first node or this node, this element, if I take this is the first node, then I can take the appropriate boundary condition and find out. So, let me take the elements now. So, let me take this simple element where I let us take this side also. You can take this side also. So, here W is 0 and your EI d2W dx2 is also 0, right. And what is the boundary condition here? Here the slope is 0 and obviously there is no shear force. So, that is dw dx actually 0. So, dw dx is this is L by 2. So, this will be 0. Now, to compare this frequency, we need to if I want to compare it with respect to the critical frequency, then I can I have to know the critical exact frequency of this beam. So, which is P critical is your exact is your pi square EI by L square, I think. So, this will come around pi square is 9.48 or something, 87, 9.87 EI by L square. This will be the this thing. Now, if I do the exact solution of this beam, then the standard stiffness matrix, again the standard stiffness matrix I need to consider, that is 2EI by L cube, and then this is 6 minus 3L, then minus 6, then minus 3L, then 4L squared, then 3L, then L squared, then this is 6, 3L, then this is 2L square. Sorry, this is 2L square. So this is 2L square. 2 is outside. So now this is my beam stiffness matrix, and Kg is also we have derived in the last class. So the Kgij is essentially integral 0 to L dV dx into dw dx. So, or if I write it in terms of shape functions, that is d phi I dx d phi j dx into dx. So, this is into dx, but let me write it. So, this is actually your K G I J. So, ijth entry we can compute, and that is actually your 1 by 30L divided by then 36 minus 3L minus 36, then minus 3L. So, you need not to remember this, because generally you can know the form, how it will be symmetric matrix, we all know. And if you try remembering this thing is very easy, because some of you have noticed probably that in your BTech or graduate undergraduate level, you have learned what is the beam stiffness, that is how we computed beam stiffness, that is 2L EI by L cube is a stiffness and all those things. So, remembering this matrix is very easy, but remembering this matrix is little bit difficult. So, obviously no one is actually try to remember it, because finite element solutions are mainly computer based. So, we can always code it and increase our accuracy. So, these are two these things. So, now if you solve this problem and if you now take node number 1 and node number 2, so your vectors, W vectors will look like this. So, this will look like W1 theta 1, W2 theta 2. So, if you this will be 0 and this will be 0. So, these two term only appear. So, these terms will go out, these terms will go out, and naturally only this portion of the matrix is our effective matrix. So, if I just write it, so the eigenvalue problem will look like similarly this part will be effective. So, the eigenvalue problem will be determinant of det of this matrix 2EI by L cube, 2L squared, 3L, 3L, 6, then minus PCR, then this will be 4L PCR by 30L, then 4L squared, 3L, then 3L 36. So, this will be your 0, determinant of this matrix will be 0. So, this will give us the characteristics equation. So, I have just computed it. So, the characteristics equation you can find out, that is 45 lambda square minus 26 lambda, then plus 1 equals to 0. So, now here lambda is defined like this, that is L squared by 60 EI into PCR. So, this is the value of lambda, actually just multiplying and equating it to 0. So, now if I find out the solution, lambda 1 2, that is actually 13 plus minus root over 124 by 45. So, this actually gives me the smallest eigenvalue, which is naturally the smallest one is 13 minus root 124 by 45, which is actually 0.04133. Now, this is our lambda. So, this is the smallest critical load. Now, this lambda, if I just use this lambda to compute the now critical load, so which will come around PCR, so which will come around your 9.9439 EI by L square, where the exact one, as I told you earlier, is I think 9.87 EI by L square. If you look carefully, that critical buckling load is approaching from top. So, that means these calculations, so the approaching top from means this load is higher than this load, exact load. So, that means we can use it for design. So, we will be always in the higher side. So, approximate solution, it is important that the approximate solution, if we take it from the higher side, that is this load will always be safer buckling load compared to this, because the exact load is less than the approximate load. So, this is it. So, you can compute buckling load for any structure. For instance, pin I have done. So, 1N pin, 1N fixed you can do, or any custom setting you can change. Even today's there are some in online, you will find out some calculators also which can calculate the buckling load given the values of EI and L square and all those things. So, this is a small problem I wanted to discuss. Another thing I want to discuss is that if you have remembered that I told you that the general beam column equation will look like this, that is d2 by dx square EI d2w dx square plus p into d2w by dx square equals to qx. So, this is a beam column equation. Now, if I just want to do a free vibration problem, for instance, a beam with a axial force. Now, if I want to find out its free vibration or the natural frequencies or mode shapes or the fundamental frequency, then this problem can be appropriately modified. For instance, for free vibration problem, so here the objective is to find out the natural frequency, not the critical buckling load. So, you have to remember that because when I do the critical buckling, then P is my unknown. So, here P is known to me. So, for instance, the same beam, if I know the if I want to find out what is the natural frequency for this beam given this P. So, important thing is P is given here, okay. P is given here. So, here it is not finding out the critical buckling load. The objective of this is finding out the first fundamental frequency and or the other frequencies and the your mode shapes. So here as I did for the beam case, it is just simply a modification. So this will be my term, then additionally we will have the inertia term into it, and I am just taking the damping term 0. So d2w d2 dx squared ei d2w dx squared plus p. So here I am not writing CR because p is known to us. So d2w dx squared, then that will be rho a omega square. So omega is the natural frequency that we need to find out, and then we'll have your the displacement w. So that is our equation. So now if I wanted to find out the weak form of this equation, then as usual way we can find out the weak form of this equation. The weak form is same because this term will not be participated in the integration by parts. So naturally this term will not create any boundary condition term. So the boundary condition terms will be as usual. Now only difference is that here a mass matrix will also appear. So finally if you do the weak form and then you discretize with the Hermite shape functions, then what you will get, the equilibrium equation you will get. I am just writing the discrete form because you can do, I believe now, the weak form of this, because we have already seen this is for beam term only beam problem. Now we are doing it for beam column problem, where the axial vibration of the or the vibration of the beam column problem. So now here Ke is the standard bending stiffness will be there, and due to that there will be a geometric stiffness. So naturally minus P into your geometric stiffness Kg will be there, and then due to this there will be a mass matrix term. So here it will be omega square, that is into me. So this will give me my final eigenvalue problem, which will have w again, and then this will be 0. So this is my eigenvalue problem. So here P is known to me, and my objective is to find out W. So mass matrix also we know, Kg we know, mass matrix also we know for the beam problem, that is Me. I think rho A by rho AL by 420, then 156 minus 22L, then 54, then 13L, then this is 4L squared minus 13L, then minus 3L squared. So this is consistent mass matrix. So 22L and then 4L squared. So this is my mass matrix. So additionally you have to just put this term. So now as like the previous problem, we have to find out the eigenvalue of this problem. So this finding out eigenvalue of this problem means eigenvalue and mode shapes obviously. So this determinant of this matrix has to go 0. So now you will find out the characteristics equation, and then from this characteristics equation smallest eigenvalue will give you the fundamental frequency or the first natural frequency of this problem. So this is an additional problem which you just need to modify. So the objective is you have to know the governing differential equation. So now the finite element procedure is pretty same, because your mass, geometric stiffness and bending stiffness, all three terms we all know. then only thing is that here you have to remember that here the force is specified. So, we are not really finding out the Euler-Buckling law, rather we are finding out the frequency of the system. So, then once you find out the frequency, you can calculate the mode shapes, and based on your number of element, you will get the number of frequencies, because number of element will decide your number of degrees of freedom in the system. So, number of frequencies you will get, and the corresponding mode shapes, first mode shape, second mode shape, and so on. So, those will be approximate mode shapes. There are some problems which exactly we know. So, it will be much better if you can compare, or if you can code these problems in a small programming language like Python and other things. So, you can just compare with the exact results that probably you have studied in your stability classes. So, that's all. So, I want to end here today. So, in the next class we will start a another module. So, till then let us meet in the next class. Thank you.